process of the phosphate recovery from wastewaters using magnesium alloy plates. In this study, we used magnesium alloy plates dipped into ammonium dihydrogen phosphate solutions to acquire mainly acquire struvite in the first studies, but why we used ammonium dihydrogen phosphate? Ammonium dihydrogen phosphate is similar to wastewaters, so we use this chemical to mimic the wastewater systems. And firstly, I want to talk about the phosphorus. Phosphorus is the element most abundant material in the Earth's crust, but currently this phosphorus acquired from the phosphate mines, and in the next 100 years it's said to be extinct in this, depleted in these mines, and our main source is these phosphate mines. And when we look at the other elements, the most abundant 10 elements in the Earth's crust, only the iron can suppress this tons of phosphorus mined in a year. So this shows that phosphorus is mainly comes from the phosphate mine sources, and in the next 100 years these can be depleted, and our main source is these phosphate mines. And but the phosphor and phosphate is actually quite common in nature. We have phosphorus in ourselves. The vegetables have phosphorus. Of course, there is always phosphorus somewhere, but we cannot take this free phosphorus from directly from nature. So we want to somehow acquire this free phosphorus. And the other subject is purification. In wastewater systems, currently phosphorus and nitrogen elements are directly poured into our seas, and this can lead to purification. Phosphorus and nitrogen are causes a feeding frenzy in the upper regions on the sea, and this purification is blocks the sunlight and oxygen to plants, seaweeds in the water, and they kill fish. Because of that, we need to somehow stop this. In the recent years, this is not so important. Before these years, like 5 years ago, I suppose, we firstly see the mucilage in our seas, like in Marmara Sea or Aegean Sea. We see this mucilage is actually this purification in our seas. So why this is caused? It's caused by the wastewaters mainly, from the industry, from our homes. These wastewaters directly goes into sea. So this should be stopped, and this is my little samples. The right one is like purification in sea, left one is normal, and in this study we aim to take these elements from the wastewaters and protect the nature and have these minerals and use them in a effective way. So we want to achieve this. In the literature, they used magnesium chloride salts mainly in swine waters and wastewaters to acquire steroid and other phosphates. But we, in this study, when we started, we aim to achieve fully conversion from magnesium alloy plates to superwhite. Our preliminary studies shows us that steroid can be acquired by dipping the magnesium alloy plates into ammonium dihydrogen phosphate solution. And in the mainly they are using magnesium salts, and they precipitate the superwhite inside these systems. The only plates used in these literature studies are, I found out that this study uses magnesium alloy plates directly, but they are using galvanic anode as these magnesium alloys to acquire superwhite. This is actually a good example. The high purity superwhite is directly acquired by this, but this is not so cost effective because we need to use electricity, and it is not cheap. Our study is novel in this area because we are not using magnesium chloride, but magnesium plates itself, and we are using just chemical reactions to acquire this superwhite or other phosphate conversion. But our aim is to have a monolithic conversion of these magnesium plates and primarily have a superwhite in our first aim. In our experimental setup, we use different alloys, AZ31 and ZX31, and as a reference, pure magnesium ingot. And we use different thicknesses from these samples. We have actually have a different mechanical histories of these samples too. For example, for AZ31, we have S-cast in ingot form and hot rolled plate form, and again hot rolled plate form, but annealed to have a stress relief on the structure. So in order to acquire this annealing, we subjected some of our magnesium alloy plates to 400 degrees Celsius about an hour, and in order to have a high concentration of ammonium dihydrogen phosphate and magnesium solution, we increase the temperature to 35 degrees Celsius. And one set of the samples, the 12 of them, subjected to ambient cyclic temperature, and the others subjected to 35 degrees constant temperature. And here it can be seen in the furnaces we annealed our subject. This is our experimental setup, two sets. So what we have found out in the first in the first 10 minutes in first hour, we found out that the rapid hydrogen gas evolution from this ambient ambient temperature gradients. This graph shows us that first hour of immersion of our samples in ambient